So, let us study affine sets. So, this I already answered. A set is affine if contains okay. So, your set is affine if you pick any 2 points in that set and the line containing it or the affine combination of those 2 points are still in the set itself. That is the affine set, and it is not hard to argue using induction that this definition can be changed to a set is affine if all possible affine combinations of points in S are in S. So, there is no good reason to restrict taking a affine combination just any 2 points. You can take any number of points in S, take their affine combination and things will not change. Yes, it is not obvious, but you can make it work. Sorry, this is the definition. Pick your favorite. Okay. Countably finite. Yeah. We are in reals, so those things are fine. Those things are a problem if you take integers and things like that. But in a real space, these things do not matter. Good. Yes. Good. That is the next question. That is what we are going to solve, right? But once again, the question Soham has in his mind is, what does the affine space look like? Seems like a difficult question. So, what do we do? Examples. Good. And we have taken already one example. If I take 2 points, their affine combination is a line, right? What if I take 3 points? It is a line? Okay. So, that is a good generalization, but did you really understand how you prove it? Chalo. Okay. So, assertion is, and I guess that is because you believe in the beauty of mathematics. So, you say, yeah, if it is a line, let us say plane through the 3 points, but then as the ugly part of mathematics, we need to prove it. Very good, right. This is what we want to study, where alpha 1 plus alpha 2 plus alpha 3 equal to 1, right. This is the set we want to study. And as Dev has planned, it has actually a very nice representation where I can say this is alpha 1 times x1 minus x3 plus alpha 2 times x2 minus x3 plus is this correct? Or just x3? Sorry. Okay, sounds good. And the important point here is alpha 1 and alpha 2 are and now you have gotten your answer. What is this? This is the plane spanned by by x1 minus x3 and x2 minus x3. This we already know, right? This is just a plain linear combination of x1 minus x3 and x2 minus x3 because alpha 1 and alpha 2 are unrestricted. This we already know. And now the structure of this is very simple. You take x3 and put the plane through it, plane on top of it. So it is a plane with an offset. Okay. And not surprisingly, you can do this trick with any affine set, right? X is some point in R to the n, and V belongs to some vector space. Okay, so this is for all x and for all vector spaces. So you fix an x, you fix a vector space, you define your subspace like this. Sorry, I should not say this. And you can easily prove that this is an affine set. So a translation of a plane, or a, sorry, I should say a linear subspace, is an affine subspace. A translation of and since I can do this trick for any number of points, it is going to turn out that even reverse is true. So what is an affine set? It is offset plus a vector space. Okay, and in my favorite two dimensions, it looks like this. This is my offset, and then if I translate this line to here, that is going to be my vector space. Remember, this is not a vector space. If I pass it through 0, then it is a vector space, right? That you can easily see that if you look at all points, you know, alpha v, this is a vector space. But if I move that line, that doesn't remain a vector space, right? But all your affine sets look like this. And now, if you look at this definition, these two things seem important. It turns out actually not. The offset is not really important. The vector space always remains the same. You can actually choose this offset, you can choose this offset, you can actually choose any point in the affine set as the offset. And this is true. I could have played the same trick with x1, right? I could have played the same trick with x2. So even though it looks like it is offset plus a vector space, it's any offset in the affine set adding the vector space, and that's because of the linear combination structure. Sounds good? Do we have a good understanding of what an affine set is now? Because before you go to convex sets, you understand affine sets, no? And we have to understand convex sets because linear programming requires convex sets. The feasible region is going to be a convex set. So now, this is one kind of a, for the lack of the better term, duality here, in the sense there are two descriptions of a affine set. right? One description is, sorry, right, no, but that and this, yeah, that is true. That's kind of a way to define it, but I don't think we ever use it. That's not very useful definition to use. So one is this offset plus vector space, and the other is, you know, how to describe a line. You write an equation for it. For an affine set, it is going to be what we call a hyperplane, which is okay. So again, this both natures, I can write it as an equation, I can write it as a geometric object. Now this is an affine set, is not hard to prove. Other way is also not hard, right? Because what is this saying? This is saying that every x which has a constant inner product with A, correct? Right? This is saying that my inner product with B is constant. Now again, this would have been easy. What is this? This is the things which are perpendicular to A, right? This, now let's say x0 is a point in this, then this is x0. So let's say this was the case. You have an x0, an offset, A transpose x0 will give you B. You can add any V to it such that A transpose V equal to B, right? So this is the vector space which is perpendicular to A, moved in some direction. And again the same thing, the vector space remains the same. You can't change the vector space, that's the important part. It is the perpendicular vector space to A. x0, pick any point such that A transpose x equal to B, right? So in multiple ways we see the same thing, but this is the important trick. This is the trick which we will play again and again for almost all the geometric things. We will have a geometric picture and an equation picture. Sounds good? Now we move to convex sets. I should talk about conic sets also, but that's not very important. I will talk about cones later. They are slightly difficult. You have to be very careful while you define conic sets or cones. That we will do later. Today we understand convex sets. Any questions about affine sets? Good? Okay, great. What is the definition? A set is convex if it contains the line segment. Okay, natural, the way we did the affine, right? And no prize for guessing. Theorem, yeah, you can take convex combination of multiple points also. I won't go through it because that's basically an exercise in induction. But once we define this, another important thing is what we call convex hull. So, given a set S, convex hull of S, this is the notation, is the set of all convex combinations of S. Okay. So, what is the convex hull of 2 points? Line segment. That's okay, right? This we have seen multiple times. That's the simplest case. But in general, I can have multiple points. And if I take convex combination of everything, everything in that set S, that's called the convex hull of S, right? And also, now what can happen? Suppose with these 3 points, I take a convex combination, I get a point here. With these 3 points, I get a convex combination, this is here. Now I can possibly take convex combination of these 2 points again. What do you think? Is this a convex combination of these 4 points? Yes, it is. Do I need to prove that? You can all do it, right? You have 2 set of coefficients, each of them you kind of multiply by, let's say, half and half or 1 by 3, 2 by 3, still they will remain positive, they will sum up to 1. What does this prove? Convex hull is convex. Too many convex things, but yeah, convex hull is convex, right? Even though I just took the convex combination of S, these are going to be vertices, but this is fine. And this might again look complicated, but you have seen these things. Like affine set turned out to be just vector space and offset. Similarly, convex hull, see, generally a convex shape could be very, very complicated, very hard to describe. A circle is a convex set because you take 2 points inside the circle, the line segment stays inside, right? This is convex, or at least the shape I intended to draw was convex, right? Convex. No? Oh, sorry. Yeah, right? And to be able to describe it in, every possible way, this is going to be, it is convex in my eyes. Okay. So, but it is very hard to describe it if you want to describe it by equations. We will take the simpler task. We will talk about convex hull of finite many points, and that is going to be reasonable enough. Okay. So now I have 3 points. How will the convex hull look like? Why? Okay. Start, this line has to be there, this line has to be there, this line has to be there. Is it convex yet? No. I can take these points, entire triangle. Good. I was hoping that you asked this question, because then I can tell my next theorem. Convex hull is the smallest set or I should say, do I want to write it as intersection? Yeah, is this? It's the smallest or if you want to think about it, take all possible sets which are convex and contain S, take their intersection. That is going to be convex. So let me write it. All these are equivalent definitions. Okay? So this is a valid point. What is the guarantee that I haven't left out anything? This is a convex set. This contains 3 points. That is enough. So that means I just need to prove this theorem. Take 2 minutes and prove this. It's not hard. It's like a 2-line proof. It basically says that you are not confused between all these convex, 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 convex. Sorry? That's the next thing I'm going to talk about. But again, I'm not going to talk about it because you will prove it. It's like the simplest thing. Right? Again, if there are 2 points, if they are in both the sets, their line segment will be in both the sets. It will be in the intersection. So then, right? So every so if it is S1, S2, S10, S1 will contain the line segment, S2 will contain the line segment, S10 will contain the line segment. So the intersection will contain the line segment. That's all. But we go there later. So think of any set which contains S, right? Now it contains S. It's a convex set. That means it will contain all the convex combinations of S. Okay. So take S. Oh, sorry. Take T containing S. Take any set which contains S. Now, if T is convex, it contains all convex combinations of S. That means it contains convex hull of S. That means T is bigger than convex hull of S. Simple? Okay? Again, these definitions might seem out of line or slightly confusing, but there is something geometrically which is very, very simple. So it's just to make sure that you align your geometric intuition with these definitions. And if there are any questions, I would be happy to answer or give them as exercise. Right? So we had affine sets. Affine sets were linear subspaces by an offset. Right? Now we are talking about convex sets. Look like a triangle. If I take 4, it will look like mostly a quadrilateral, sometimes a triangle. Right? So if I take 4 points, great. This is the convex set, right? When I mean all this. If I take a point inside, still remains the same, right? And now, what do you think? Intuitively, can you describe to me what is convex of S if this is a finite set? What's again, I don't want it to be mathematically correct. In your mind, what is the picture? For 4, it was a quadrilateral, something which has kind of a boundary lines, right? It might happen that the number of vertices, number of extreme points are not equal to S because some of the points can get inside, but in some sense, I look at all the points, I look at all the outer points and connect them by straight lines. That's called a thank you, polygon or Okay, so the difference is this is bounded. Okay, so what do I mean to say? So actually for finite set of points, this will always be a polygon. Okay, that means it will be bounded, but we will be interested sometimes in convex sets which are slight extension of polygons, right? So polygon is okay, right? Polygon like this. Okay, but we might sometimes be interested in convex sets which go like the previous thing was bounded, this is unbounded, right? What is the mathematical definition of a set being bounded? What do you think it should be? Good, so you have seen it before. So there is a big ball. So there is a big ball, you can say from origin, which contains the entire set of finite radius. There is a sphere of finite radius which contains my set. So in case my set was like this, there is a big ball. So basically you are not going to infinity, right? So again, simple intuition, I have to give a mathematical definition to all these things. Bounded, okay? So polygon is bounded, polytope is unbounded, but something whose boundaries are these straight lines, and it's a convex set. But again we will see these two things coincide. And before I proceed further and forum objects, intersection of two convex sets, convex. Similarly, union of two convex sets, not convex. Each of you draw an example. Why can't you draw in your paper? I don't think that's a good enough excuse. Everyone keep a pen and a paper with you. It helps in my class at least. Please try these things. I know you are ultra smart. As I always say, what is the best thing about UGs? They give very quick incorrect answers. Right? So let's try to make them correct. And the simple thing is to think before you are answering. So everyone can draw two convex sets such that their union is not convex, right? Good. Simply put, you take any two disjoint convex sets, their union is not going to be convex. Good? Okay. Sorry? No, union is convex. And intersection is also convex. So, good. Sorry?